So it's May Day today, but we have to have a lecture, and this is a lecture 17. Okay, but I hope that we can make a relatively short lecture today. I hope. Okay, so let's begin our previous last lecture. So, um, we spent quite a long time about the derivation of the expression for our current density. So the problem was, so when we consider three different regions in our PN junction, then what we can calculate out of our simplified expression was just minority carrier flux. So for example, let's say that this is a p-type and this is an n-type, and in between we have a space charge region. Then what we can say is we know the electron flux inside this minority carrier region. Also, in the case of a hole, we know the flux in this minority carrier region, n-type region. However, in order to calculate the total current density, we must calculate Jn evaluated at a certain position and Jp evaluated at the same position. This x and this x, these two x values should be the same. At the same point, we must measure the electron current density and hole current density. But unfortunately, the information we are understanding is just restricted to this part and that part. So at which position we can calculate the sum of Jn and Jp. It's not possible in principle. So what we did was, so we cannot do that, but instead of that we made a bold approximation. Why don't you just assume that this one is just constant over space charge region, and now we know the same value of flux even at the starting point of this space charge region. Once we assume such kind of approximation, then just summing these two terms, then we will get the current density, which is constant all over our entire system. So maybe you feel it has some weakness in our theory. We have assumed that the flux does not change inside this space charge region. Then how can we justify ourselves? Actually, we cannot. So we have to introduce additional things. So today we will do such kind of thing. So in our last night, last time we had an online office hour, and a student asked me whether net generation is occurring or net recombination is occurring in this space charge region. But in our so in our currently considered forward bias mode, then we can say even in this part we have net recombination, both of course electrons and holes. Then it is quite easy to understand the situation. Simply speaking, let's have a look at this one. We know this value. This value is a known value, and let's assume that there is a certain amount of net recombination. I mean that actually recombination is specified as recombination rate. So what is recombination rate? It is in a dimension of a number of electrons or holes which is recombined at a given unit time. That is a usual unit of our net recombination. However, what we wanted to know is, here we have a finite length of our depletion region. So net recombination can be distributed. For example, let's draw one typical example like this. At this point, we have a most significant recombination. At these and these points, the recombination can be relatively low. When we have such kind of distribution of net recombination, then in order to quantify the total number of carriers recombined during the journey of our electrons from here to here, it should be integrated. So simply speaking, we have to integrate our net recombination rate over what? Over the depletion layer. So this lower part should be the beginning point of our depletion layer, and this upper limit should be the ending point of our depletion layer. If we make such kind of an integration, then we will measure some quantities. When this quantity is integrated once along x direction, then what will be the unit of that quantity? You understand that will be the quantity something like this. What is it? Per unit area, per unit time, how many electrons or how many holes are recombined and disappear from conduction band or the valence band. That is quantified by this simple integration. So now let's think about quite strange numbers. For example, here we know that, so every second, so there 100 electrons are passing through this position. And let's assume that inside in this system, for example, this is just example, this number are not relevant, but let's say that we have 50 electrons per unit area and unit second, they are disappearing. Then my question is, then what will be the injection flux measured at this point? Everybody can assume that that should be just 150. Okay. Otherwise, observe that if this is not 150, then there is some contradiction. There is 150 electrons comes in, and among them, 1/3 of them is recombined, and only 2/3 of them just escape from this depletion region and enter into this n-type region. So simply, quite simply, please note that what we have to do is to measure both of electron current density and hole current density at a same position. That is the requirement. So what we have to do is like this. In order to measure the electron flux and hole flux at a given position, for example, this position, what we have to do is, hole flux, we already know it. So the only thing we have to do is move our known electron flux into this position, from here to that position. How can you do that? As we have done just before, please add the integrated net recombination. Then we will have the flux evaluated at this point. By summing these two terms, eventually we will get the flux which is constant all over our system. That's the point. So now you understand the reason why we have this additional form. This additional form was introduced just to describe the integrated net recombination form. So, okay, simply speaking, let me just say it this way. Oh, there is some tunnel, and in tunnel, there what happens, and some electrons are killed. So what we have to do is, okay, since there is 50 electrons in every second they are killed, so in order to get 100 electrons surviving from this depletion layer, then we have to supply 150 electrons into this system. That is the perspective from cathode. Okay. So now we understand. Okay, but yes, this quantity and this quantity can be well quantified, and we already have done it. Everybody now understand it has the form of exponential of our applied voltage divided by summer voltage minus 1. That is the form of our current component originated from this Fn and Fp. Now our remaining task is actually evaluate this quantity. Well, then everybody can understand this is not an easy task, because when you do such kind of integration, first of all you have to understand what is the form of R over X and G over X. Well, then it means that in order to understand this quantity, then you have to assume certain form of your, I'm going to say, electrostatic potential, and even in quite a simple case, it just looks like a parabola. So you remember, potential just looks parabola. So that would be quite cumbersome. So instead of that, in our textbook, we just introduced a quite reasonable approximation. Please note that this current component is not a wanted one. Oh, I like this recombination component. No. So because this is just unwanted one. Why it is not wanted, that will become quite clear. So anyway, usually we don't want it. So what we wanted to do is not precisely determine the level of this value, but instead of that, we wanted to know the upper limit of this value. If something is unwanted one, what we have to do, or what we usually do, is to have certain safe range for our application. In a worst case, what will be the value obtained from that unwanted phenomena? So therefore, in our approximation, we wanted to calculate the maximum value or upper limit of net recombination instead of precisely calculating all kinds of this recombination, because that can be time dependent quantity. However, we wanted to do something like this. Please have a look at this one. This one is the maximum value and multiplied by the length of our integration domain. So let's just come back. Instead, let me just draw once again. Let's assume that our net recombination just looks like this, for example. Then what we are doing in this next stage is, instead of considering all of this integration, but just to pick up the maximum value and just to calculate the area underneath of this horizontal line. Then you can easily understand our calculation will overestimate the value obtained from the exact integration, but doesn't matter because what we wanted to do is just to see the functional form of our net recombination rate. Okay, are you with me? So of course, if you wanted to do it precisely, accurately, then you have to use your computer program. But you know, sometimes we have to be a little bit careful about that. So at a certain position, we have to move into the computer simulation in order to get the qualitative, quantitative result. But where will you stop and where will you give up? That really depends on your decision. Somebody can just learn only basic principle and just learn many calculation without thinking about the physics. Then he or she will get tons of data and just believe it because the God says, okay, this is your result. This is one thing. However, even better one is to study this system as much as possible with human understandable way. Only after you fully understand others know, then you switch to the computer simulation. So please, I want to recommend you to more concentrate on this analytic understanding. Okay. Of course, eventually you have to move to the calculation. Well, anyway, now that was a simple justification of this crude approximation. Instead of evaluating the position dependent G and R, we will just use this quite a simple form. And let's go to this way. Then our task becomes quite simple. We must calculate the maximum value of this net recombination. Then where do we have the maximum net recombination? That is the point. Then okay, so this form net recombination is given by, of course we have a certain certain coefficient which depends on many different things, but most important one is simply given by this product, NP minus Ni square product, the difference between NP and Ni square. As I told you repeatedly, if this is larger than 0, then it indicates that excessive carriers are coming into the scene. So that will introduce our net recombination. On the other hand, if we have net negative term, it means that okay, we have no electrons and holes. So now the summer excitation through the SRH recombination center will be seen, and it will be or interpreted as net generation. Okay, so that is the simple rule. Then we have to consider this one. Well, how large is it? So here in the depletion region, the MP product is simply given by Ni squared times exponential normalized applied voltage. It is because actually we must have the difference between phi p and phi n. However, following our current assumption, this whole quasi-Fermi potential is nothing but just voltage applied to our anode contact, and this one is also corresponding to the voltage at our cathode contact. What is this? The difference between anode voltage and cathode voltage. that was defined as applied voltage in our approximation, in our setting. So by the way, please hold on. I will check whether my voice is recorded okay. So safely recorded. Okay, so simply speaking, in the depletion region, so this upper term is a constant. Wow. And this is constant, and the position dependency of our net recombination only comes from what? Only comes from this one. And this Ni is intrinsic carrier density. This is a constant, and in order to maximize this overall net recombination, then we have to, in order to maximize it, then we have to minimize it, and this is a constant. So what we have to do is we have to find out the position where the sum of electron density and hole density is minimized. So are you all with me? So let's say that happen to be our NP product is, for example, corresponding to 10 to the 23, and let's say, let's assume this case. Well, usually at equilibrium we have, for example, something like this, and instead of that, since we are now considering slightly forward biased diode, then let's say that we have 1000 times higher NP product than our Ni square. Then in this case, now think about this case. This is the assumption, but consider two different positions. At one position, your electron density is 10 to the just 14. Then what will be your hole density? Your hole density will be just 10 to the 9. If you have 10 to the 10 here, your hole density is 10 to the 13. So in order to minimize this number, what will be your value for electron density and hole density? It is quite certain that in order to minimize it, actually you must have N equal to P equal to 10 to the 11.5. Okay, so are you with me? So approximately it will be 3 times 10 to the 11. In this case, the sum of your electron density and hole density would be just 6 times 10 to the 13. For other cases, that will be just 10 to the 14, or this one will be 10 to the 13. Oh, so I made mistakes in the order, not 13, but here we have 11. So sorry about that. So here we have the sum of electron density corresponding to 6 times 10 to the 11, and this is 14 and 13, way higher than this minimum value. So simply speaking, in order to maximize this recombination rate, we must find out where electron density and hole density are balanced. So therefore you can find that this is nothing, there is nothing, this is here, the condition is now our N equal to P equal to just square root of Ni square exponential we apply divided by summer voltage. So you can now insert this form into your N and P, then that will give you this expression. Okay? So simply speaking, the maximum net recombination rate follows certain coefficient, but this coefficient is not that important because we have already made certain enveloping for our integration. In order to perform, instead of performing the exact integration, we already introduced certain envelope for its maximum value, so its leading coefficient is not that important, and please concentrate on this functional form, dependency on your applied voltage, and you can find that actually looks quite similar, exponential of our applied voltage, but please note that there is a significant difference here. Have this term. Why do we have just number 2 instead of number 1? It was originated from the value of electron densities in the lower part of this expression. So in order to have the maximum value, actually our electron density, at this balancing point, the electron density just not increasing following e to the v applied by 1 times the summer voltage, but it is increasing 2 times the summer voltage as a normalization factor. So that's the reason why we have this form. So now let's go to the final result. In the previous lecture, we have considered the sum of diffusion current. That was already given, and it looks certain behavior, exponentially increasing behavior. And today we have talked about this term originated from net recombination, and we have found that actually its form is simply given by V applied. However, here we have a different normalization constant, and it is just simply 2 times summer voltage. So therefore, if we increase our applied voltage, this diode current and this space charge current will react differently. For example, let's say that both of them, let's consider, for example, 0.3 volt, and both of them shows quite balanced values. I diode was quite similar with I space charge region, and now let's say that instead of this one, if we go to 0.36 volt, oh sorry about that, instead of this number, why don't you just consider this one, 0.42 volt. Please estimate the increase of your current values. So at 0.3 volt, both of them shows more or less comparable values. After that, if we increase just 120 millivolt, then from our dependency, like e to the applied voltage normalized by summer voltage, we can expect that there will be 100 times increase in our diode current. We'll see later. But in the case of our space charge current, the increasement is not like 100 times. It will increase only by factor of just Why? Because here we have a factor 2 in its input argument, so just happened in the logarithmic scale. So simply say, if we draw, for example, this is applied bias voltage, and this is the current component, both of diode current and space charge current. In this example, let's say that we have a 0.3 volt, and both of them shows similar value. Let's say that this, instead of just a linear scale of current, take please log 10 of current density, current itself. So therefore we are now drawing semi-logarithmic graph. Then this example means that if we increase our applied voltage to 0.42, just 120 volt, then what we can expect is, okay, there will be 2 orders of magnitude increase in our diode current. At the same time, our space charge current will be just 10 times higher. So simply speaking, diode current quickly overcoming this space charge current. Well, so it is not that important. No, it is not the case. Please think in a reverse way. Instead of increasing the voltage by 112 millivolt, please think about the case where we have go the negative direction, so our voltage now becomes, instead of this number, please think about 118 volt. Then what will happen? The diode current once again will decrease quite quickly, so our diode current is now once again 100 times smaller than the value at 0.3. So this is what we wanted to do. We wanted to do precisely control the current by the applied voltage. When we apply higher voltage, then we wanted to have a steep increase of current, and when we decrease the voltage, then we wanted to have steep reduction of our current. However, as you can see here, this behavior simply means that, especially this is the space charge current, means that even when we approach it to lowly biased, or the diode closely biased quite closely to the 0 volt, even in that case we will have the remaining current component out of space charges. So that is the point. We wanted to shut down the device. However, there is some remaining term originated from this net recombination. So we must understand this one. Okay. So of course, we have studied these 2 different behaviors, like just to follow summer voltage or 2 times summer voltage. But in reality, when you measure the actual IV characteristics, then this value is not precisely 1 or not precisely 2. That is measured in between, and of course it depends on the bias you apply. So therefore, instead of setting 1 or 2, people wanted to introduce a certain variable number and just to use it to fit your IV characteristics. Okay. So do you have any question? If you have a question, then please let me know. So this is nothing but in order to explain you the diode IV characteristics. The main message is here we have a diode. All of these six graphs are corresponding to just one diode, and there is nothing but what I did is just draw same graph with different maximum value. I just set 1 microamp as the maximum value for this graph, and here we have 100 milliamp for the maximum value of this IV graph. So if I just delete all kinds of numbers attached to y-axis and x-axis, can you recognize any difference? So no one can recognize the difference. So simply speaking, diode is just quantified as described as these two distinctive behavior. Below certain voltage, we don't know the exact value, but anyway, there is almost no current. However, if we have a certain voltage close to its turn-on voltage, then it just explodes. It means that the diode current just explodes. Almost a vertical line is obtained for this number. Okay, so therefore, simply if we have, for example, a diode and a resistor here, and if we apply certain voltage, then if our applied voltage is so small, then for example even smaller than 0.5 volt, then what will happen? It is not possible to turn on our diode. Then since diode is not turned on, it does not conduct any current. I is quite close to 0. So since there is no current conduction is allowed, then we will have almost every voltage will be applied to this guy. Okay, so now let's go to this one. Previous description was just linear IV characteristics. This was voltage and this is a current, but it is just current, linear current. However, instead of this linear current, we wanted to draw also current in logarithmic scale. Take the log 10 of current, we will have more or less straight line, because you know this one just follows exponential of our input voltage. So take the log 10, then we will have just a straight line. Important one is, I think that most of you already understand this number, but if you don't remember this number, I wanted to emphasize once again. There is very important one shown here. I have introduced those red dots to indicate the point where we have 10 times higher terminal current. For example, this red dot is assigned to 10 to the minus 8, and this second dot is corresponding to 10 to the minus 7. In order to have 10 times higher current, larger current, how much we additionally apply the voltage? The voltage difference is given by this. So can you read the difference? Or in order to increase your current from 10 to the minus 7 to 10 to the minus 6, 10 times higher, then we must also apply this amount of additional voltage. and you can find that this voltage, the voltage required to increase your current 10 times, that is approximately 60 millivolt. Please note that 60 millivolt. 60 millivolt is, when you just write down in volt unit, it is just 0.06 volt. Oh, do you feel this is a large number or small number? But when you consider just 1 volt, 2 volt, or at large numbers, then that can be regarded as a quite small differences. So simply speaking, with a small additional voltage into your diode, you can conduct quite a larger current. For example, following this one, for example, my quick question is, if you apply 0.3 volt additionally to your diode, then how much do you expect the increasing factor of your terminal current? The answer would be just 10 to the 5, because you know this 0.3 is corresponding to 300 millivolt, and this is 5 times larger than our unit 60 millivolt. So every 60 millivolt we have 10 times larger current, so we go 5 times with this step, so we will have 10 to the 5 for our step. Of course, please note that this is just diode analysis. We are not still reaching at the MOSFET, the device we have to consider eventually. But this lesson is same between this diode and MOSFET. Even MOSFET, we have the same behavior. In order to increase your current 10 times, you need, at room temperature, you need 60 millivolt. And 60 millivolt is not that large voltage difference, so we can quickly turn on and turn off our device with a small voltage difference. So that is the one. And up to now we have thought about the behavior of a diode, and the thing we have not covered yet is, also not covered in this lecture material, is it's a reverse biased diode. Fortunately, our equation derived for forward bias mode can be safely applied also to the reverse bias one, so that's the reason why we do not treat it additionally or separately. So please read your textbook, then you will see the similar expression. Maybe you may think that what is the form of actually electron density, hole density, or recombination or generation. So I will make a quite a short summary. In this reverse biased case, then let's say that this is our p-type region. At equilibrium, we must have this constant value corresponding to n sub p, minority electron density in the p-type region. This is the equilibrium case, and up to now we have considered the forward biased case, so always we have thought about this kind of behavior. We have additional excess carriers, but when you apply the reverse bias, then now instead of this one, now you have even smaller number of your electron density. Why? Because our law of junction still valid in the reverse bias mode, so now we have smaller electron density. So what will happen now? Our relatively small electrons here will diffuse. Well, think about this one. for example 10 to the 17 per cubic centimeter of p-type doping density, then this will be just 10 to the 3 per cubic centimeter. And now we will have even smaller values at this point. So although values are quite small, however there will be certain density gradient. So electrons will diffuse into this way. Once it approaches to this boundary, then here we have quite a strong electric field. So that electric field just takes the electron and send it back to its homeland called as N-type region. So that will be the origin of a reverse current, quite a small reverse current in our diode. Okay, so since the numbers are just 10 to the 3 or something like that, please think about the magnitude of your reverse current. So when you apply the bias, then you can easily increase it by factor of 5 or even higher. For example, just applying 0.3 will increase your minority carrier density by factor of 10 to the 5 orders magnitude. So you will have quite a severe behavior of your excessive charge carrier. However, if you apply reverse bias, then what will happen? Yes, it will decrease, but the value you can expect as its minimum value is just 0. It does not go to the negative value. So even though you apply strong reverse bias voltage to your diode, but you cannot make a big difference in your reverse bias current. Okay, so that's the reason why when you draw your IV curve here, when you draw your IV curve for diode in this forward bias mode, you expect quite a dynamic behavior. However, in your why we have such a steep change, because your excessive minor carrier varies quite steeply with respect to applied bias. However, in the case of a reverse one, there is almost nothing, because once again excessive minority carrier density cannot go to negative value, and this difference is so much small, so we cannot derive much current. Okay, so that was a simple note on our reverse bias junction. I will not deeply talk about this one, and we have to discuss about short diode. As I told you before, our main discussion was for long diode. It means that our injected electrons, for example, when electrons are injected into this minority region, then we have a sufficiently long length to be recombined fully and finally arrive at the anode contact. However, if we have quite a short p-type region length, then there is no exponential function allowed, because before taking full recombination, our electrons just arrive at this anode. This is the starting point, and that is the ending point, the finish line. And with this movement, we expect a certain kind of reduction due to certain recombination phenomena. However, since this is just one step away, so there is no chance for having meaningful recombination. In this case, the expected behavior of our electron density, excessive one, is no longer exponential. It's just expected as a linear function. In this case, actually the important length scale is now changed from previously important length scale was this one, electron diffusion length. It was related with the diffusion constant of our electrons and also tau n, the minority lifetime. However, in this case, in this opposite case, this recombination does not play any significant role. Now instead of that, important one becomes just a physical width of your p-type reason. So if you just make it short, then you will have higher current, because when this is given, and if you just make the length half, then you will have much steeper behavior of your minority carrier density. Then that is directly affecting 2 times the increase of your diode current. Okay. So we will have this form. Okay, that was the discussion about IV characteristics of our PN diode. Okay, so now we have to go to the switching property. But before talking about switching property, today I wanted to talk about, first of all, the linearization of our electronic device. So this is a so important concept. So that's the reason why I'm introducing this concept, although it is not explicitly covered in our textbook, Professor Tower's book, but I wanted to discuss about it. Okay, linearized system. So think about this one. Our device, for example, what is a device? PN junction or MOSFET. In general, they are nonlinear. Nonlinear means that here we have input and output variable. When we insert the input variable into our system, then it generates a certain output value. However, mathematically, the relation between input and output are a non-linear function in general. Typical example, think about our diode. You know, y equal to exponential over x. What is it? This is nothing but the diode current is exponentially dependent on what? Dependent on voltage divided by summer voltage. So please regard this x as a normalized voltage and this y as also normalized current. Simply speaking, up to now we have spent quite a long time about diode IV characteristics, and they can be modeled as a simple exponential function. So then I have actually two questions. Now let's assume that we wanted to calculate y value. We want to still calculate y, but let's assume x is given by 24 certain number, time independent number, and sum over 24 and 12 times sine omega t. Here omega is angular frequency and 2 pi times frequency. So if we visualize x first of all, what will happen? Can you draw your, this is a time and this is your x, then can you draw it? Of course you can. when you draw this function, then you will have first of all 24. Then how about this sine term? With the sine term, you will have this form. Okay. My question is, please just try to describe this form, this waveform, lead solid line. Then you will say that, okay, it has an average value of 24, and it looks like a sinusoidal function, and its amplitude is about 12. Then that will be your description about your x value. What is x? X is your input. Then my next question is, then please perform the calculation, evaluation of your y. Once again, function of time. Then what will happen? So can you draw it? Of course, yes, using computer program you can do it, but let's just try to make something. We can consider some representative points here. For example, here at this point we have x equal to 36, and here we have x value corresponding to 24, and here we have x corresponding to just 12. Then how does these 3 points will give you the value? The expected value is exponential over 36, exponential over 24, exponential over 12. Which one is the largest? Exponential over 36. Which one is the lowest? Exponential over 12. But my point is not that one. Please draw it. When you draw it in a linear scale, how does it look like? You will just have one value corresponding to exponential over 36, and other two values, exponential over 24, exponential over 12, that cannot be recognized as non-zero value. You will have just a vanishing value. So what you can expect out of this discussion is eventually your graph will just look like, in my opinion and from my own experience, your result will just look like this. Of course, these peak points are appearing at these points. Then my question is, please try to once again describe, instead of the input variable, now please describe the output variable with your language. Then what will happen? Can you say it is still averaged at exponential of 24? Its average is 24, and we have an amplitude of something. Can you say so? And it is still a sinusoidal function. You never say in that way. It is just like a pulse. And we are losing our sinusoidal property. So the shape of our output variable is completely different to that of our original input argument. This is the case, and this is a difficult case. But now think about different one. Here, now we have a different case like still the average value is 24, but amplitude is now just given as 0.04. Please try to override on it, then you will draw in this. Oh, sorry about my ugly drawing, but anyway, that will be the shape of our second example. Then please try to draw your y function. So you can do it, please. Then you will recognize that in this case, even your y value just looks like just a combination of your average value and a sinusoidal function. That is the point. So for example, let's think about this one. Here we have input argument, which is the combination of x naught and delta x. Here, what is the x naught? In our example, it was 24. And what is the delta x? In our example, it was 12 times sine omega t, or 0.04 sine omega t. So in this setting, please do the Taylor expansion. When we do the Taylor expansion of exponential x naught plus delta x, we can do it in this way, exponential, and we just take x naught, and it is given by 1 plus delta x, x naught. So exponential sum of, I think that so I'm a little confused, so I will make my correction. So so this part will be discussed later, but point is, let's come back to once again, I'm a little bit confused. So when we come back to our example here, when we have small amplitude about our additional function, then we are allowed it to have Taylor expansion. However, if we have large amplitude for this sinusoidal term, it is not allowed it to have this Taylor series expansion. So when we are allowed it to do such kind of linear expansion, then now we can say this way: we just supply this signal with a certain angular frequency, and the output will also have the output signal with angular frequency omega. What is it? This is nothing but we apply sine omega t, and the final result will also y contains sine omega t. Please, I wanted to recommend you, please draw this example by yourself, also this example by yourself. You will find the clear distinction between these two cases. The system itself is just kept as y equal to exponential x. We have not changed the system itself. The only thing we have done is, instead of supplying large amplitude input signal, but we just consider small input signal into it, then the behavior of our system seems to change, although its essential point is not changed, but we can approximate as a linear system. So that's the reason why we say linearized system. This is a passive term. Originally it is a non-linear system, but we treat it as linear system by only supplying small amplitude input. That is important. So practically, what is it? So if you have, for example, a diode, then you can apply the voltage. For example, let's say that this is grounded and you apply certain V apply. In this case, you can, for example, consider 0.3 volt as a DC voltage. However, also in addition to this number, you can apply additionally 1 millivolt sine omega t. If you have this form, then what is your DC term? This term is 0.3. And what is the amplitude of your small signal additional perturbation? That is corresponding to just 1 millivolt. Since 1 millivolt is a relatively small quantity, then now you can use this kind of small signal analysis. So what you can expect is, since this is small, this system can be linearized, and you expect also your diode current will contain the current originated from your 0.3 volt application, and also small current induced by this AC excitation. So you will have this small delta I. Then the relation between this 1 millivolt and this delta I can be expected and found. That makes certain kind of information. Of course, there is one more complication. Although I have written like delta I times sine omega t, but unfortunately there may happen like cosine omega t. So delta IC should have sine component and cosine component. Or sometimes we introduce complex number phasor to think about this sine component and cosine component. But anyway, the essential point is, when we have a small input, then the system can be linearized, and for this linearized, the input signature is just kept. So if you insert the signal with angular frequency omega, then your output signal will also have angular frequency omega. Okay. Before finishing our today's lecture, then let's come back once again our general case. Do you think that this one is linear or non-linear? Of course, this is non-linear. And now let's say that you have x equal to 1 plus sine omega t. Instead of that 0.001 sine omega t. In this case, what you can do is y equal to x squared, but it can be well approximated as y equal to 1 plus 2x. So you may say that, okay, y is well approximated as 1 plus 2. So sorry about that. Here we have only small signal component. so x minus 1, so we have to have 2 times 0.002 sine omega t. That will be the answer. Well, I'm just repeating the linearization of one simple nonlinear system, but instead of that, now let's say that we have 1. Number 1. Then what will happen? Please explicitly calculate the output without relying on the approximation. Then your y will be just the square of 1 plus sine omega t square. Without eliminating anything with approximation, you will have 2 times sine omega t. You have already covered it in your approximated form, but point is now you have a square of sine omega t, and you know that this is corresponding to the angular frequency of not omega, but it is corresponding to 2 times omega. From this quite simple example, I mean that in a general system, general nonlinear system, when you insert a signal with angular frequency omega, then usually what we can expect out of the general system is not linearized general nonlinear system. Then you may have signal at omega and signal at 2 omega, signal at 3 omega, and integer multiples of your fundamental frequency omega. That is the point. So generally nonlinear system can generate a lot of frequency component corresponding to the multiples of fundamental frequency omega. They are called as harmonics. However, so we can make so many harmonics out of one fundamental signal. However, for linearized system, then all of these higher harmonics components have quite small amplitude and can be safely neglected. That's the reason why we can consider just a one-to-one correspondence between input signal and output signal with having the same angular frequency. Okay, so as I announced, next Monday we have no lecture, and next Wednesday we will quickly cover the switching property, but quite quickly, only qualitatively, and now we will enter into the discussion about the long-awaited MOS structure. So MOSFET will be covered from the next lecture. Thank you.